Let us understand analog to digital converter of LPC2148. The features of ADC available in LPC2148 are it has 10-bit successive approximation analog to digital converter. There are two ADCs available in LPC2148. These are named as ADC0 and ADC1. We can use power down mode of ADC. When these ADCs are not in use, you can enter it into power down mode. Then the V reference voltage for ADC can be generally used as a 3 volt. So the output voltage range can be from 0 to V reference. The conversion time for 10-bit output is 2.44 microsecond. The bus conversion mode is also available for single or multiple input. So continuously we can apply input and we can ADC can convert it into digital output. The basic clock used for AD converter is provided by APB, that is Advanced Peripheral Bus. Then fully accurate conversion requires 11 clocks. So if we want a 10-bit output, then we require 11 clocks. If we need a less bit output, means 9-bit or 8-bit output, the less number of clocks will be used. So these are the features of ADC used for LPC2148. There are two ADCs, AD0 and AD1. All pins of AD0 are not used. Here it is shown the pins AD0.1 to AD0.4, that means AD0.0 is not available, and AD0.6 to AD0.7. These many pins of ADC0 are available for user. So user can connect analog inputs to any of this pin or to all of this pin. Then the second ADC, which is 8-bit ADC. So all pins of this ADC are available for user AD1.0 to AD1.7. V reference voltage is available, VDD-A, that is analog for analog input. So that power supply voltage we have to connect, and VSS is the ground terminal. These are the pin numbers used for this ADC inputs. AD0.1 pin number 13 is used, AD0.2 14. So like that, these are the pin numbers. V reference voltage is of 63 pin, VDD is 7 pin number 7, VSS is pin number 59. Here we can observe that each pin is having multiple function. For example, AD0.1 can be used as a port terminal P0.28. It can be used as an input for ADC, for capture, compare mode, like that. So most of the pins are multiplex. Now if we want to interface this ADC to any analog input or any sensor, we can use this type of interfacing. So in this diagram, pin 0.28, that is AD0.1 is used. So to this pin, voltage divider is connected externally. So here pot is connected. By varying this pot, we can vary input analog voltage. Internal ADC will convert this analog voltage into digital, and that digital output can be displayed on this LCD. So here LCD is interface D0 to D7 as a data bus of LCD. Here the ADC output may be of 10 bit, but we are sending over lower 8 bit to this LCD. This is register select terminal, read write terminal, enable terminal. These are the terminals of ADC. So to display this output, we can interface LCD, or you can display output on LEDs also. Now let us go through the different registers used for ADC programming. The first register is to select the function of port pin to which we are going to connect input voltage. So first register is pin select register, which will select the function of particular port pin. So if we are using AD0.1, so it is of pin number 28. So we have to use pin select register 1, pin cell 1 register. So this is suppose 32-bit pin select register. So 2 bits are used for each pin. So for pin 28, so these 2 bits are used, D25 and D24. So to select the function of this pin as analog input, we have to store here 0, 1, logic 0 for D5 bit and logic 1 for D24 bit. So we are connecting, as an example, we are connecting input to AD0.1. So we have to initialize this 2 bit 0, 1. 0, 1 means for pin 28, we are selecting function as analog input. So this pin select register we have to initialize. So if you store 00 for all other bits, we have to initialize it with value 01 000000. We'll convert it into hex, and in pin select register we have to store this data. The second register is AD0CR register or AD1CR register. Since in this example we are using ADC0, so we'll initialize AD0's control register, CR's control register. So this is the format for AD0 control register. So I'll discuss it the different fields of this register. First, this select field, bit number 0 to bit number 7. This is used to select the ADC0 channel. So we are going to use channel ADC01. So we have to store here 00000010. So this bit should be 1 because we are using ADC 0.1. So pin number 1 we are using. So this corresponding bit should be 1. If we are using ADC 0.2, then this bit we have to set as 1. So for this field we have to store 01000000. So select the particular channel of ADC. Next is clock division. So suppose we'll assume that the desired clock for ADC is 3 megahertz. We want a 3 megahertz clock signal. Then we have to use this formula to find this clock division field. So peripheral clock divided by ADC clock minus 1. Here peripheral clock is suppose assume as 15 megahertz. So we'll substitute here 15 megahertz divided by ADC clock is 3 megahertz and minus 1. So if you compute it, you will get a 4. That 4 is in decimal. So we'll convert it into binary and we'll get 00000100. So for clock field, we'll have to store this data. Next bit is the burst bit. So if it is 1, then AD converter does repeated conversion. So if you don't want to do a repeated conversion, then this bit should be 0. So it will just read a 1 input and convert it into digital output. If it is stored as 1, it can read a continuous input data and convert it into digital. The next fields are related to clock. So how clock signals you need? So that is given here. If these 3 bits are 0000, then 11 clock signals are required and output is of 10 bits. If it is 001, then 10 clocks are required, but output is not of 10 bit, it will be a 9 bit. So perfect output if you want, that means 10 bit output, then 11 clocks it will use and you have to initialize this field with 000. Similarly for other, if you want 3 bit output, so you require only 4 clock and you have to initialize it with 111. But you won't get a proper output if you use a 3 bit output. So here you will get a perfect output and here you will get a very less, means the output is not at all perfect, only 3 bit output you will get. So clock field we have to initialize accordingly. Then PWM, it is power down field. So if it is 1, the AD conversion is operational, means it is performing some operation. 0 means it is ideal, not doing anything. So it has entered into power down mode. The next bit is start, 24 to 26 bit number. So to start the conversion, we have to store here 001. So if this field is 001, then the conversion will be started. If it is 000, the conversion won't start. So to start the ADC conversion, you have to store this field as 001. The next is age field, bit number 27. If it is 1, start conversion on falling edge of the selected cap and match signal. So that is related to timer and capture and match signal operation. If it is 0, then it starts on the rising edge. So if you initialize all these bits of this control register, these 4 bits are for start, that we are going to store 001 if you want to start it. Then 11 clocks if we want, then we'll initialize this field. Then clock is divided by 4. Then selection bits. So if you initialize according to your need or application, then we can initialize this AD0CR register. Now here this one is with a start of conversion. If start of conversion is also given while initializing this, then you have to write here 1. Otherwise you can write here 0 initially, and whenever you want to start a conversion, you can store this field as 001. So that can also be done. So according to your application, you can initialize this register, ADC control register. The next register is ADC Global Data Register. So it is ADGDR register, and these are the bits of this register. 0 to 5 bits are reserved, and from bit number 6 to 15, 10 bit result will be stored. Now first let us see about this done bit. This bit is set to 1 when an AD conversion is complete. So when ADC has completed its conversion, then automatically this done bit will be set to 1. So user can check whether this done bit is 1 or not. If it is 1, it indicates that conversion is over and the 10 bit result is stored in result field. So we can check this 10 bits for the output. Overrun, if there is some error or anything, the working is not proper, this bit is set to 1. Then reserve, these bits are reserved. Then CHN is channel number. This is a done bit. So for channel, these bits contain the channel from which the result bits were converted. So if it is 00, then it is channel 0. If 001, then channel is 1, like that. Channel number will be stored here. So this is the register where we can check whether conversion is over or not. and if conversion is over, result will be stored in the 10 bits. Now let's see how the simple program of ADC conversion. We have to initialize all these register. So initialize pin cell 1 register. Here we are configuring this ADC 0.1 pin as a analog input pin for input to this ADC. So that is initialized. As you know, we are using here OR function. So we don't want to disturb function of other pins. Then the direction register we are going to use. So if you are interfacing LCD, if you are interfacing LED, according to that you can select the direction of pins. Then we have to initialize AD0CR control register. So here start of conversion is not initialized. This bit is 0, so start of conversion is not given. All other bits are initialized according to application. In next step, the start of conversion is initialized. That means now after this, the conversion will be started and we don't want to disturb other bits. So we have used here OR operation. If you want, you can initialize start of conversion during this instruction also. But here the start of conversion is initialized afterward. Now we have to check whether the done bit is 1 or not. So for that, what is done here, we'll read this contents of this GDR register. So the GDR register contents are ANDed with this value. We are interested only in done bit. So done bit is MSB bit. So that we are ANDing with 1. Done bit is ANDed with 1 and all other bits are ANDed with 0. So final result will get only done bit as it is and all other bits will be 0. So if the result of this AND operation is not equal to this 8000, that means if done bit is not 1, then it will continuously execute this instruction. So we are using a while instruction. In every program we have used instruction like this. If done bit is 1, that means conversion is over. So it will go to next instruction. In next instruction, what is done? This contents of AD0 GDR register are ANDed with this FFC0 value. Why it is ANDed with this value? Because now we are interested only in result. Result we are interested and result is from 6 bit onwards, 10 bits from 6 bit result is stored. So we are ANDing other bits with 0 and only this FFC, these many bits are 1. So we'll get only result bits as it is, other bits will be 0. And since result is stored from 6 bit, we have shifted this result by 6 bit in right direction. So result 10 bit will be at the LSB position. So get a result bit at LSB position, we have shifted it right by 6 bit. So now our 10 bit result is at LSB position. So first we ANDed it with FFC 0, all other bits will be 0, only bits of result, 10 bits of result will be as it is, but since result is stored from 6 bit, we are shifting this result 6 bit in a right direction. So result is now stored as a LSB. Now this result you can send to any port terminal. So here IO0 set 08 port is used. So whatever bits are 1 in the result that we want to set. So value as it is given to IO0 set. We'll complement it because other bits we want to clear. So IO0 clear. It's complemented and then it is given to clear register. And while one program is ended here, you can connect LEDs to this port 0 and we can check the output on LEDs. So in almost all program we have used this logic. For example, suppose you want to set, I am considering only 4 bits. Actually it is 32 bit or 10 bit. So if you want to set this 3 bits, so we'll send this data as it is to set register. Here I am considering only 4-bit data. It is same for 8-bit, 10-bit, 16-bit. So we want to set this register. We will send this value as it is to set register and we want to clear this. This bit we want to clear. So to clear this bit, we'll complement this number. So we'll get number as 0, 1, 0, 0. And then we'll store this data in clear register. So what will happen? Only this bit for which we have written 1 will be clear. All other bits will remain as it is. So this is the simple program for ADC.